All right, we're going to take a little bit of time and look at some of the weird stuff that happens with the electron configuration of D block elements. The first oddity, which I'll call it, is the number for n for our D blocks. It's always going to be n minus 1 for the D block elements. And what I mean by this is let's look at this periodic table. So, you know, n here for these rows are 1, 2, and 3. Now, when we get to 4, that 4 applies to the first two columns and then these last six. But when we get to the D block, it's going to be n minus 1. Put it like this, n minus 1 for our D block. And so this first row of D block would be the 3D elements. And then this would be 4D and 5D and so on. Now, what's even more weird is when you get to the F block, because the F block is kind of like the D block, except the F block is n minus 2. And kind of note how most periodic tables kind of do this, where they have this like empty space right here, and they say 57 through 71. Well, what we're really doing is taking all of these elements and forcing them up into those two rows. And so really the periodic table should be a lot longer than the typical one. It's just that the reason they put those F block ones down at the bottom usually is because they're not as commonly used. And we very rarely talk about them in general chemistry. And overall in the science field, like they're just not dealt with a whole lot. And so they kind of like put them as almost like a footnote at the end of the periodic table. But when it comes to their notation, they always go n minus 2. So if n here is 5, 6, 7, for the first row in the F block, this is going to be 3F. I'm sorry, 4F. And this is going to be 5F. So that's just one thing you have to keep in mind if you're doing electron configurations that are going lower than n equals 3. So let's do an example of this. And let's look at manganese, Mn. So that is over here. I'm just going to erase this. Here's manganese. Manganese is number 25, so 25 electrons. Now I'm going to show you something cool that you can do with electron configurations. And you're allowed to do this for, atoms that go below the third row. So I say this a lot in my OChem class, but chemists sometimes are lazy. And so if we can shorthand stuff, we're going to do it. And what we can do in electron configuration is rather than write out all of the stuff, all the previous electron configuration. So like the electron configuration for the first three rows would look like this. 1s2, 3s2, I'm sorry, 2s2, 2p6, 3s2, 3p6. That takes care of the first three rows. Now, I can shorthand all of that and use this convention. I put the noble gas that represents. So it's the noble gas, that's these guys right here, right before the element you're looking at. So if I'm looking at manganese, the noble gas right before it is argon. And I just put that element in brackets. And that just tells the reader that I'm shorthanding all of that electron configuration up to argon, and I'm basically going to start on the fourth row. So now my electron configuration starts here at 4s2. So I'm gonna just kind of erase this here. So 4s1, 4s2, and then I'm counting over 1, 2, 3, 4, 5 spaces to get to manganese. Now again, I'm starting at 3D. That's n minus 1. So my configuration ends in 3D5. Now let's do another example. Let's look at iodine. Iodine is here, number 53. And rather than draw out every single electron, I'm going to go to the noble gas right before it, which is krypton. Yep, there's an element named krypton, just like the planet. And I'm going to put it in brackets. I'm telling the reader it's start off with the configuration all the way up to krypton, and now I'm going to start on row number 5. So 5s2. So I've gone all the way there. And then I'm counting over 10 spaces to get through the D block. Again, it's n minus 1, so 4s10. And then I go back to 5 for the p subshell. So 5p5. Okay, so that's kind of the weird thing, just one of the weird things to remember with when you're going through the D block is it's always n minus 1 when you're representing um, the D subshell. And I just made a mistake there. I should say 4D10, not S, 4D10. Now, weird thing number 2, half-filled shells are energetically more favorable. And the reason for this is electrons, if they can avoid being paired up, they're going to want to like have their own room. Because think about it, electrons have a negative charge. If I try to force two negatively charged things to be close to each other, what do they want to do? They're going to repel. And so with some of these D block elements, I'm going to erase a lot of this here. Weird things kind of happen in periodically, and those periods are very set. So, like for example, let's look at chromium. Now, if I draw the assumed electron configuration of chromium, so I'll start off with argon, noble gas right before it, 4s2, and then 3d4. Let's draw out the orbital configuration for that. Starting here on s, so 4s, and then I have 5 3d orbitals. I put 2 in the 4s, and I put 4 in the 3d. Again, I'm following Hund's rule that says I have to half fill everything before I start to completely fill them. But I want you to notice, like, this is not the most energetically favorable version of chromium. Because if I were to take that electron that I just circled in the 4s and give it to the 3d, what does that look like? I now have a lot of half-filled orbitals, which is energetically a lot more favorable than not having half-filled orbitals. And so my real electron configuration isn't this. The correct electron configuration for chromium would be 4s1, 3d5. And that's going to be true. You're going to see that a very similar trend to all of these atoms right here in that column. Now, something else is going to happen very similar to that when we get to these elements, like copper, silver, and gold. If I do the electron configuration for copper, again, I'm going to start with argon and then 4s2. And notice it's 9 spaces over. So for 3d9, remember n minus 1. So if I draw the orbital diagram for that, this is what I originally come out to. Now it's energetically more favored to have this subshell be unpaired. So I'm going to move this electron over to the 3D subshell. And so the 4s is half filled, and my 3D is completely filled. So the correct electron configuration for copper is 4s1, 3d10. And again, I want to highlight, you're going to see that with this column, copper, silver, and gold. And then finally, weird thing number 3, I kind of touched on, but I'll highlight it here. Dealing with the F subshell. And remember, the reason why the F subshell is kind of weird is because it's like they were taken out of the middle of the periodic table and then placed down here. So let me show you how we deal with an element that goes into the F subshell. So we're going to use bismuth here, number 83. Okay, now I don't want to draw out all 83 electrons. So I'm going to be, you know, a lazy chemistry person and use the shorthand. So the noble gas right before it is xenon. And then let's start here at our 6s. So 6s2. And notice we get to this empty box here. What that means is I'm going right to the first row of the F block. And again, with F, it's always n minus 1. So I'm going through the whole F block. So that's 4s14. And then I'm going to go back to D. Well, what row is this for D? That is 5D. 5D10. Oops, I went a little too far on that. And then I'm going into 3 on the 6p3. Remember, S and P are always the same number. D block is n minus 1. F block is n minus 2. Now, finally, let's talk about the electron configuration of ions. This process is exactly the same as it was for neutral atoms. The only thing we're doing is just adding or subtracting electrons. So let's take oxygen with a -2 charge. Okay, so normally oxygen neutral has 8 electrons. Now it has 10 electrons. So let's go through our order here. Start with 1s2. So went through all of that. And then we go 2s2. And now we're into the 2p. Now, normal neutral oxygen would end at 2p4, but it has 2 more electrons. So I'm going to make it 2p6. Now let's look at calcium. Calcium has a common, when it's an ion, um, it almost always has a +2 charge to it. And think back, if something is negatively charged, it gained electrons. How does something become positively charged? It doesn't gain protons. Remember, we don't deal with adding or taking away protons. We only deal with adding or taking away electrons. So that calcium lost electrons. So if calcium here, number 20, has 20 protons, it should have 20 electrons if it's neutral. But it lost 2, so it will only have 18 electrons. Okay, well, let's go through the configuration from the top. So 1s2, 2s2, 2p6, and then I'm going to go to the third row, 3s2, 3p6. Now, if calcium were neutral, I would say 4s2. But it's a cation. It lost 2 electrons. Where am I going to take those electrons from? I'm always going to take them from the highest energy level. So there they are. Actually, I'll do it this way. They're gone. Okay, we don't show anything about 4s in the electron configuration. So the calcium +2 ion has that configuration. Now, finally, let's look at the D block elements. The D block metals are going to lose their s electrons first. And here's what I mean by this. Let's look at iron. So here's iron. I'm going to use the shorthand here. So I'm going to use the normal gas right before ion, which is argon. And then it's 4s2, 3d6. Now the iron, one of the common cations for iron is with a +3 charge. So what has to happen in order for it to be +3? Well, it's got to lose 3 electrons. So let me just start off by drawing it neutral again. So it's always going to start by taking those 3 electrons from S, the S subshell first. So I'm going to take away both of those. And I'm going to take away, or the only other place I can take it away right now is the D. So the electron configuration for iron with a +3 charge is just 3d5. All right, that's where we'll conclude with electron configuration.